Welcome back to the deep dive. You know, usually when I sit down with the prep material for these sessions, I'm looking for the big concepts, the aha moments. But today, I barely got past the first page because I hit a statistic that just, it made me put my coffee down.
I have a feeling I know exactly which one you're talking about.
Oh, yeah.
Was it the muscle activation one?
It was the muscle activation stat.
Yeah.
For everyone listening, just try and wrap your head around this number. A single human life involves roughly 10 to the power of 13 distinct muscle activations.
A 1 with 13 zeros.
I mean, it's a number so large, it stops feeling like math and starts feeling like noise.
It really does.
Exactly. And the source makes this incredible comparison. It says even a generic 2-week vacation to Hawaii, just that one trip involves roughly 10 to the power of 10 motor actions.
10 billion.
10 billion. So my immediate thought was, how on earth does an AI plan for that? It can't possibly sit in the server room and pre-calculate 10 billion muscle twitches before it decides to, book a flight.
It absolutely can't. If an AI tried to plan at that level of detail, muscle twitch by muscle twitch, I mean, the universe would probably suffer heat death before the robot even made it out the front door.
Right.
And that is the central tension of the chapter we're unpacking today, planning and acting in the real world.
Because up until now, the AI planning we've looked at has been pretty sterile, hasn't it?
Oh, very sterile.
It's always pick up block A, put it on block B.
Right. We call that the vacuum world. In those models, there's no traffic, no deadlines, things don't break.
And nobody else is messing up your carefully laid plans.
Exactly. But the real world is messy. It has ticking clocks, limited resources, and half the time you can't even see what you're doing.
So our mission today is to figure out how AI bridges that gap. How do we go from a huge goal like build a car down to the chaotic reality of actually moving motors without, melting the processor?
And what's fascinating to me is that the solutions AI researchers came up with look suspiciously like how we manage our own lives.
We don't plan muscle twitches either.
Not at all.
Let's start with that first big headache, time. The source material draws a really hard line between planning and scheduling. And I feel like in normal conversation, I use those interchangeably.
Most people do.
If I say I'm planning my day, I usually mean I'm putting times on a calendar.
Right. But in AI architecture, they are very distinct phases, and for a good reason. Think of it this way. A plan is just a logical sequence. It tells you what to do.
Okay, so put on socks, then put on shoes.
Exactly. It's about causal order. Scheduling adds the time and the resource constraints. It asks when are you doing it and what tools are you using.
And the source advocates for a plan first, schedule later strategy. Why split them up? Why not just figure it all out at once?
Because of the math, the computational complexity. If you tried to figure out the exact timestamp for every single action while you were still figuring out the logical order, the possibilities just explode.
It becomes impossible.
Totally. You'd get stuck analyzing whether putting socks on at 8.01 is fundamentally different from 8.02.
So you get the logic straight, first socks, then shoes.
Yeah.
And you worry about the clock later.
Precisely. You select the actions to create a valid sequence. Then you add the temporal constraints to make sure you aren't trying to use the same machine for two things at once.
The text uses that car assembly line as the example.
But job shop scheduling problem.
Right. We have actions like add engine, add wheels, inspect, and then resources. Hoists, wrenches, inspectors.
Standard manufacturing stuff. But this is where the complexity creeps in. Suppose you have a task that requires an inspector.
Okay. And this is where they introduced that concept of aggregation. It sounded like corporate buzzword bingo at first, but it seems to be a mathematical lifesaver.
It is absolutely a lifesaver. Let's say you have 10 inspectors on the assembly line. You got Bob, Alice, Steve.
Right.
If your scheduler treats them as 10 unique individuals, it has to check every single combination. What if Bob checks car A? What if Alice checks car A?
Oh, that doesn't seem too hard.
With 10 people, that's 10 factorial. That is roughly 3.6 million combinations just to assign people to tasks.
Okay, point taken. That is a lot of wasted computing power just to decide who holds the clipboard.
Exactly. So aggregation means you stop viewing them as Bob and Alice. You view them as a pool.
Inspectors. Quantity 10.
Right. You treat the resource like a fluid. If you need 2 units of inspector and you have 2 available, you just proceed. You don't care who it is.
That turns a problem with 3.6 million possibilities into just one calculation.
Instantly solvable.
All right, so we've aggregated our resources. We have our plan. Now we hit the critical path. I hear project managers use this term all the time, usually when they're panicking.
They usually are, yeah.
What does it actually mean in the math?
Imagine all your tasks laid out on a timeline. Some can happen in parallel, right? You can put the front wheels on while someone else puts on the back wheels.
Sure. They don't block each other.
But some are sequential. You can't inspect the car until the engine is in. The critical path is just the longest single sequence of those dependent steps from start to finish. It's the absolute minimum time required for the whole job.
It's the bottleneck.
It is the bottleneck. It determines the project duration. If you shave an hour off a task that isn't on the critical path, the project doesn't finish any sooner.
You're just standing around waiting at the end.
But if anything on the critical path gets delayed by 1 minute.
The whole project is late.
Exactly. And this introduces the concept of slack.
Which is what I'm usually looking for on a Friday afternoon.
Right. In scheduling terms, slack is the window of time an action can be delayed without pushing back the final deadline.
So a task on the critical path.
By definition, has zero slack.
Zero slack. That sounds stressful.
It is. But for an AI, calculating slack is crucial. It tells the system where to prioritize. If you have a resource conflict, say you only have one wrench, you take it away from the task with slack and give it to the one on the critical path.
Because the slack task can wait, the critical path cannot. That actually seems like good life advice.
It really is.
Okay, that handles the when and the with what. But let's zoom back out to that Hawaii example. An AI cannot plan 10 billion muscle movements. So how does it actually plan a vacation?
We use hierarchies. This is arguably the most human-like aspect of this whole thing. We don't think in muscle twitches, we think in high-level actions, HLAs.
So go to San Francisco Airport is an HLA.
Yes, it's a single blob of action.
Yep.
And that HLA breaks down or decomposes into smaller actions.
Like drive to parking, park, take shuttle.
And drive to parking breaks down into start car, back out of a driveway, all the way down until you hit primitive actions that the system can just execute without thinking.
This is called a hierarchical task network, HTN.
That's it. It's recursive.
This seems really efficient. But the source mentioned a specific problem with this that I found, well, fascinating. It's about angel versus demon semantics.
Oh, I love this part. It sounds so theological, but it's really about probability and control.
Okay, so break it down for me. The AI is looking at a high-level blob like go to airport. It doesn't know the details yet.
Right. And because it's vague, there's uncertainty. Suppose the HLA go to airport could be done by taking a taxi or could be done by driving yourself.
No.
But taking a taxi requires cash, and you might not have cash.
So there's a chance of failure.
Exactly. Now, if you are using demonic semantics, you're the ultimate pessimist. You assume the environment is an adversary. You assume that if a choice can go wrong, a demon will make sure it does go wrong.
So the demonic view says, hey, there's a version of go to airport where you're stuck without cash, so this whole plan is unsafe.
And it rejects the plan, throws it out.
But that's paralyzing. You'll never leave the house because something could always go wrong.
Exactly. Demonic semantics are way too strict for real life, which is where angelic semantics come in.
The optimist.
The optimist. The angelic view remembers a key detail. You are the one making the choices.
Right. I'm the one deciding whether to drive or take a taxi. The demon isn't choosing for me.
Correct. So the AI looks at the reachable set, all the states you could possibly end up in, and under angelic semantics, if there is at least one path through that hierarchy that works,
Like driving your own car.
then the HLA go to airport is marked as possible.
So it just ignores the path where I fail because of the taxi, because it trusts that I'm smart enough to avoid it.
Precisely. It assumes the agent behaves rationally, and this is huge. It lets the AI commit to a high-level plan without calculating every tiny step first.
The source called this the downward refinement property.
The holy grail of hierarchical planning.
Which basically
That's
means if the high-level plan says, I can get this done, then you're guaranteed to find a low-level sequence of moves that actually does it.
And that's how we plan a trip to Hawaii. We know flight to Honolulu is possible, so we put it in the calendar. We don't worry about which foot we step onto the plane with until we're at the gate.
Okay, but all of this assumes we basically know what's going on. What happens when we are, flying blind. The source transitions here into, non-deterministic domains.
A fancy way of saying the world is unknown. And this is where things get really clever.
They use the painting problem.
The classic example. You have a chair, a table, 2 paint cans. You want them to be the same color.
Simple enough.
Yeah.
But you're blind. You're sensorless. You don't know the current color of anything.
So how do you plan a solution if you can't see the state of the world?
Well, the source suggests a method called coercion, which sounds a bit aggressive.
It is. Coercion means forcing the world into a state, even if you didn't know where it started.
So the solution isn't check the colors, it's just open any can and paint everything.
Exactly. You still don't know if the chair is red or blue, but you know for a fact that the chair and the table match. You've coerced the world into the goal state.
That requires a real shift in thinking for the AI, though, doesn't it? The open world assumption.
Yes. In classical AI, if a fact isn't mentioned, it's assumed to be false.
But in the real open world,
If you don't say it, the AI has to assume it is unknown. Coercion is a way to slash through that uncertainty without needing sensors.
but of course we usually do have sensors. We have eyes, which leads to contingent planning.
Which is basically just building a decision tree. Look at the table. If it's the same color as the chair, stop. If not, open a can.
Seems obvious to us, but for an AI, the plan is no longer a straight line. It's a branching tree.
And that branching gets very expensive very fast.
So if the tree gets too big, what's the alternative? Do you just give up?
No, you do what we all do when we're walking through a crowded room. Online replanning.
Which is basically make a decent guess, start moving, and fix it if it breaks.
Right. The example in the notes was the spot welding robot.
Oh, I like this one. A robot on a car assembly line. Its job is to spot weld a door.
In a classical plan, if that door falls off the line, the robot just keeps welding empty air.
Must weld air.
Exactly. But an online replanning agent spots the failure. It realizes, oh, the preconditioned door is present is false. It stops. It switches to a gripper tool, picks up the door, puts it back.
And then resumes welding. To an observer, that robot looks incredibly intelligent.
It looks purposive, but really it's just reacting to a broken precondition.
There was a distinction here I want to nail down. The difference between action monitoring and plan monitoring.
This is a subtle but crucial difference. Action monitoring is checking the immediate step. I tried to pick up the cup. Is the cup in my hand?
So, did I drop the keys?
Right. Plan monitoring is broader. It asks, given what just happened, is the rest of my plan still going to work?
So plan monitoring is, now that I dropped the keys in the sewer, can I still get to work on time?
Perfect. And plan monitoring allows for something really delightful. Serendipity.
Serendipity.
Let's go back to the painting example. Your goal is, chair is red. But plan monitoring notices that someone else, a clumsy painter, just spilled red paint all over the chair.
A happy accident.
Plan monitoring sees the goal is already met. It realizes, wait, I can skip the painting step and go home early.
That's amazing. It's the difference between following a checklist and actually understanding the job. We've talked about robots working alone. But the final section deals with the real headache. Other people. Multi-agent planning.
The moment you add another agent, everything gets exponentially harder.
The scenario they use is doubles tennis.
It's the perfect example. You and I are partners. We share a goal. Return the ball.
But if we don't coordinate,
We might crash into each other, or, worse, we both stand there assuming the other one has it, and the ball sails right between us.
so how does AI solve this? They don't have time for a committee meeting before every serve.
No time. One way is conventions. Pre-agreed rules. In tennis, net player takes anything short.
Like drive on the right side of the road.
Right. It solves the conflict before it happens. But my favorite is communication by action.
How does that work?
If I'm your tennis partner and I start sprinting toward the net, I am communicating to you. Without saying a word, I'm telling you, I am taking the front, you cover the back.
My action is the message.
Exactly. But this coordination doesn't always need a master brain. The source gets into emergent behavior with ants.
Harvester ants. They don't have a central manager ant telling everyone what to do.
No, the queen isn't sitting there with a clipboard. But the colony has roles. Foragers, patrollers. An ant decides what to do based on local interactions. If foragers are returning super fast with food.
Other ants see that and switch their role to foraging because clearly there's a food bonanza.
The efficiency emerges from the bottom up. And we simulate this in AI with Boids.
Boids. I love Boids. The computer simulation of flocking birds, right?
Yes, developed by Reynolds. It shows how you can get that complex group motion using just 3 simple rules for each bird.
Let's list them because it's shocking how simple they are.
Rule 1, cohesion. Steer toward the average position of your neighbors. Stay with the group.
Okay, don't get lost.
Rule 2, separation. Don't get too close. Don't crash into your neighbor.
Personal space.
And rule 3.
Alignment. Steer toward the average heading of your neighbors. Go where they're going.
And just those 3 rules. No leader, no flight plan. That's it. No joint plan at all. Just those 3 local rules create complex, organized, flocking behavior. It's a powerful lesson.
It's beautiful chaos. So let's recap. We started with the sheer impossibility of planning every muscle movement, that terrifying 10 to the 13th power.
We looked at how we solve that by grouping resources aggregation and using the plan first, schedule later method.
We climbed the ladder to hierarchies and HLAs, planning the vacation, not the footsteps, and used angelic semantics to be optimistic.
Then we tackled the unknown with coercion, just paint everything, and the smart adaptability of online replanning.
And finally, we look at how agents work together, from tennis partners to the emergent flocking of boids.
It's really a tour of how intelligence copes with the friction of reality.
Before we go, there was one provocative thought from the source regarding that plan monitoring we discussed. It mentioned the dung beetle.
Ah, yes. The poor dung beetle. So if a dung beetle is rolling its prize,
Yeah.
and you take the ball away, the beetle will just keep pushing empty air.
It continues the walking motion.
It does. It lacks plan monitoring. It doesn't realize the goal is no longer achievable. It's just running a script.
Stuck in the loop.
It is. And the source implies that the definition of a truly smart agent, and hopefully a human listener, is that you notice when a plan is doomed before you finish executing it.
That's the takeaway for me. I think we all have projects where we're pushing empty air. We're doing action monitoring. I'm pushing. I'm working hard. But we aren't doing plan monitoring.
Checking if the goal is actually still there.
Exactly. Sometimes the smartest move is to stop pushing and go find a new ball.
Well said.
So, to everyone listening, take a look at your daily routine. Look for those high-level actions you're running on autopilot, and maybe check if you're operating with angelic or demonic assumptions.
And maybe watch out for any invisible walls on your critical path.
Thanks for listening to The Deep Dive. We'll catch you next time.